Okay, so the next part of the video, we're going to discuss the strategies to solve second order ODE, linear ODE. So there are four common forms of second order ODE, and these are the strategies to solve them. So the first form of the second order ODE is the homogeneous linear differential equation with constant coefficients A, B, and C. So here our coefficients are constant, just a number. So A, B, and C are numbers. So they are not a function of the independent variable, which is easier to do. So the strategy here is to use y equals to e to the mx and use characteristic equation to solve for the homogeneous linear ODE where we need to find the yc. Okay. And then the next type is we have homogeneous linear differential equation, but this time with non-constant coefficient. But the non-constant coefficients are already defined as x squared and also ax. So instead of a, b, c here as your constant, but here in this homogeneous Euler-Cauchy differential equations, you have in front of d to y dx squared, you have x squared, and in front of dy dx, you have ax. So it's already defined here, x squared and ax. So there's this particular method to solve it. So you're going to have to use x equals to e to the t and convert into I. So here we're not going to cover this in this lecture, but you can read it further using appendix 12.2 because once you convert it into this form, so meaning you are making the coefficient constant already, so you can follow the same step like what you do in the part 1 here. So the third part is, the third type is non-homogeneous linear ODE with constant coefficients A, B, C in the form of Rx here. So because it's non-homogeneous, so the right-hand side of the equation is not equals to 0, and it's a function of the independent variable Rx. So the form of Rx here is in this way, exponential of alpha x times with the, or just a combination with a polynomial of a degree n as a function of x. So we use method of undetermined coefficient for this type of ODE. And other types of non-homogeneous linear differential equations where you see here that you have p of x multiply the dy dx, and you have a q of x multiplying the y as a function of x and equal to rx. So this is non-homogeneous, and the coefficients to the derivatives are not constant. Instead, they are a function of the independent variable. So this one you cannot use the undetermined coefficient. And another case is that when rx is not in this form, not in this this form here. So you also cannot use the method of undetermined coefficient. So you need to use method of variation of parameters. So these are the strategies that we're gonna cover. So this one, number 2, number 3. So this one you just need to follow through from the appendix 12.2. Okay, so let's go through the first one, which is homogeneous linear second order ODE with constant coefficients A, B, and C. So, okay, so the mathematicians and scientists all through these years have already found out that the general solution to this kind of ODE, where A times d2y dx squared plus B times dy dx plus cy equal to 0 because it's homogeneous. So the solution is y of x, y as a function of x, equal to exponential of mx, and this one cannot be equal to 0. However, this is not a complete solution because second order problems should have two linearly independent solutions. So an analogy to this is if you have quadratic equation, okay, ax squared plus bx plus c equals to 0. So because you have quadratic, you have to have two roots, right? So two solutions, two distinct solution, or even if it's a same solution, it's repeated solution. So basically you have to have two answers. So similarly, with second order ODE, you should also have to have two linearly independent solutions. So that's why we need to find the complete solution. So how do we find the complete solution? we need to use this characteristic or auxiliary equation. Okay, so first let's obtain the characteristic equation. So we're going to derive the characteristic equation. So I think this thing here is available in your notes, but nevertheless, let's go through the derivation. Okay, so let's say you're given this ODE, second order ODE linear. Okay. Cy equals to 0, and you are given that solution to this ODE is e to the mx. So first we need to verify whether this y equals to e mx is the solution to the given ODE. So from this y, we find out what is dy dx, and we find out what is second derivative of y with respect to x. Okay, so dy dx is equal to me mx, and d to y dx squared thus equal to m squared e mx. Then we put all this thing into this ODE, the general form of the ODE. So we have a times m squared e mx plus b times m e mx plus c times e mx equal to 0. Then we can factorize the e to the mx outside and put inside here as a m squared plus b m plus c equals to 0. And since the condition is such that e to the mx is not equal to 0, then we take this term in the bracket here, am squared plus bm plus c, to be equal to 0. So this here is the characteristic equation or auxiliary equation. Auxiliary equation. Okay, so we're going to use this to find out what are the value of m. Then we can put the m inside the given proposed solution to the ODE. Okay. So, okay, yeah, we've gone through this. So we got this as the characteristic equation. So from the characteristic equation, am squared plus bm plus c equal to 0, we can determine the value of m based on the value of discriminant, just like we do when we want to solve for the quadratic equation. Okay, so if b squared minus 4ac is greater than 0, then we have real and distinct roots where m1 is not equal to m2. And if b squared minus 4ac is equal to 0, thus we will have repeated real roots, so m1 equals to m2. And if b squared minus 4ac is less than 0, thus we will have a pair of conjugate roots as the answer to m. So m1 is m plus I beta, and m2 equals to m minus I beta. So we will have to find out the values of m and beta when we do the completing the square for this kind of discriminant. Okay, so based on the values of m, so here are the values of m. So based on the different values of m, depending on the value of discriminant here, whether it's greater than 0, less than 0, or equal to 0. So if it's greater than 0, so you will have the proposed complete solution will be y equals to c1 times e to the power of m1x plus c2 times e to the power of m2x. Okay, so because you have m1 not equal to m2, so you just put it in. Okay, and for b squared minus 4ac less than 0, thus you will have the m1 as complex conjugate roots here. So m1 is m plus I beta, and m2 is m minus I beta. So your proposed solution is c1 times e m1 x. So m1 is this, and this m2 is that. Yeah. Or you can also write down this yx in terms of cos and sine. You can see the derivation for this in the appendix 12.1 from your notes. I'm just going to show you here. So appendix 12.1. Yeah. this one. So you can see here the conversion. This is Euler's definition of the exponential in terms of cos and sine. So you can go through this thing to prove to yourself that if you're given the complete solution equals to y equals to C1 M1x, C1 E M1x plus C2 E M2x, and M1 and M2 are complex conjugates, then you can write down this term as this, but A here is C1 plus C2 and B is I times C1 minus C2. So you can convince yourself how to get the values of A and B and how to write the forms from in this form to this form from the derivation here. Okay, try to just follow the derivation. It's quite straightforward. You can follow it. Okay, so yeah, go back to our slide. Right, so we are here just now. And yeah, since the value of M1 and M2 are not equal to each other, thus the proposed solution Y1 and Y2 are linearly independent. So we don't need to do any treatment to the proposed complete solution to the ODE. However, if your discriminant value b squared minus 4ac is equal to 0, then your value of m is m1 equals to m2. Thus, if you were to write y of x equals to c1 e m1x plus c2 e m2x, where m1 and m2 are the same, then this term and this term would not be linearly independent. Thus, you need to put some extra treatment. So the treatment is when you put x here. Okay, so whenever your m is a repeated real root, it's just one number, so you need to do this. Okay, so you have C1 times E times M1x, not times, it's to the power of, plus C2, and you have to add the another x value here such that the second term here is not linearly dependent with the first value in the y complementary. Okay, so the complementary solution is in EMX plus X EMX form. So the treatment is needed to avoid linearly dependent solution. And example 3. So let's do example to illustrate to you how to solve the homogeneous second order linear ODE. Okay, so let's take the first one. Okay, put it on the whiteboard. Okay, now, okay. So first of all, write down the characteristic or auxiliary equation, which is m squared plus 2m minus 3 equals to 0. And then we check the value of discriminant. So check the value of b squared minus 4ac is 2 squared minus 4 times 1 times minus 3 is 4 plus 12. Well, obviously this is greater than 0, thus you will have two distinct real roots for the solution of m. So you just factorize and find out what's the value of m. Equals to 0. So you have m1 equals to negative 3, m2 equals to 1, or vice versa. You can put m1 equals to 1 and m2 equals to negative 3. You wouldn't be penalized, okay? So the proposed complete solution is y of x equals to c1 e to d. So in general, you would write this first, right? Okay. M2x. So you just put in the value of m1 and m2. C2ex. So this is your solution for the homogeneous second order linear ODE in this example. Next example. Okay. Just bear with me. so let's do the second one. Okay. Oh, I think this is still the old one. Okay. So first step is to write the auxiliary or characteristic equation. So 4m squared plus 16m plus 17 equals to 0. Check the b squared minus 4ac. 16 squared minus 4 times 4 times 17. Yeah, just key in the number into the calculator. You will get negative 256. So this is less than 0. So you will have a complex conjugate roots. So you can try to find the complex conjugate roots by completing the squares. Okay, so you divide everything by 4 first. And then you okay, so you have m plus 2 squared plus 1 over 4 equals to 0. Then you have m plus 2 squared equals to negative 1 over 4. So m plus 2 equals to plus minus the square root of negative 1 over 4. That would be plus minus square root of 1 over 4 times I squared. Then it could be 1 plus minus 1 over 2 I. So this is m plus 2. Then you can write down m1 is negative 2 plus 1 over 2i, and m2 equals to negative 2 minus 1 over 2i. So these are your distinct roots, but it's complex numbers. So your y of x is c1 e m1x plus c2 e m2x, and your values of m1 and m2 are given here, and you put in the numbers. c1 times e times negative 2 plus 1 over 2i x plus c2 e times negative 2 minus 1 over 2i x. Or you can also write down this in terms of the cos and sine notation using the Euler's notation. So here your m value is negative 2 and your beta is 1 over 2. So you can also write down yx equal to, the general form is emx times a cos beta x plus b sine beta x, right? So you just put in your values of m and beta, e to the negative 2x times a cos 1 over 2x plus b sine 1 over 2x. So this is also correct. Either this form or this form, they are both acceptable. Okay. Next example is the third example. Okay. I think you can guess the value of the discriminant this time. So m squared minus 4m plus 4 equals to 0. Check b squared minus 4ac is a negative 4 squared minus 4 times 1 times 4. So 16 minus 16 equals to 0. So you have just repeated real roots. So you can do the factorization and find the roots. So m minus 2 and m minus 2 equals to 0. So your m1 equals to m2 equals to 2. So here, when you have this value, so you just check this one, right? Okay, so this is the case where b squared minus 4ac, so m equals to m1, m2. So your yx must be in this form. So write that down. So y of x is c1 e m1 x plus c2 x times e m2x. So c1 to the 2x plus c2x times e to x. This is your solution. Okay. Right. So example 3 done. So some overall comments. Suppose that the roots of the characteristic equations are m1 and m2, then this would be the solution for the differential equation. Okay, so this is your y1 and this is your y2. Okay, so since a d2y dx squared plus b dy dx plus cy equals to 0 is a linear homogeneous equation, by using the linear dependency and linearity principle, the general solution is like this. Basically, the overall comment here is what we have summarized in this table here. So you can just read it through. Yeah. All right. So this is the Euler-Cauchy differential equation. So where you have the homogeneous linear ODE with non-constant coefficient in the form of x squared and ax here. Okay. So here the coefficients are not constant. So the strategy is to convert the non-constant coefficient into a constant form. So how do we do that? So we need to let x equal to e to the power of t. So there's a substitution. Okay, so you need to use these two important properties to convert the non-constant coefficient into constant coefficient. So well, the idea here is you convert this x. Right, you convert this thing because it has x squared. So x squared is not a constant coefficient. So you want to convert it into a constant form. So you let x equals to e to the t and you do some dx dt, dx, or just use some y notation. Also, you can have a look at the details at appendix 12.2. And then you also convert the second term x dy dx into just dy dt. Thus, you will end up with similar like what we have in the homogeneous and constant coefficient. So we don't cover this in this class, but you can read through the steps and you can look at the appendix 12.2 and you can follow this example. So when you recognize that this is an Euler-Cauchy differential equation form, you convert and then you use the characteristic equation and then basically it's the same thing. Okay, the only different thing about Euler-Cauchy differential equation is when you have this x squared and the 3x here, then after you convert, after you've gone through step 1 and step 2, the rest are the same like what we did in the previous examples. Okay, so don't worry about it. Yeah, we'll take a short break before we go to another section of the video.